Earlier, we have made an extensive study on the solution of Schrodinger equation for one-dimensional problem. More than 20 lecture periods were spent for the one-dimensional problem. Today, we start solving Schrodinger equation in 2D. But here, we shall restrict ourselves to very few simple problems. We shall solve 2D free particle in Cartesian in x, y and r theta coordinate systems in coordinates. Then we shall study 2D infinite potential wells as in these two coordinate system in x, y and r theta coordinates, and finally we shall solve 2D harmonic oscillator. These are the five problems that we shall consider under this heading. So first we consider a free particle in Cartesian coordinate system. In the study of free particle in 1D Cartesian system, free particle in 2D Cartesian system. When we have solved the free particle in one-dimensional Cartesian system, we found that the energy of the particle has to be essentially positive and there is no energy quantization. So we consider a particle of mass m, and free particles means free particle means no force acting on it. That means V is equal to constant without any loss of generality. We assume it to be zero. So the Schrodinger equation, time independent Schrodinger equation for this is minus h line square upon 2m, where m is the mass of the particle, del 2x del x2 plus del 2y del y2 operating on a function x and y is equal to E psi of xy. What is the energy? Separation of variable technique, we opt separation of variable technique. So write psi of xt, the wave function, as x of x times y of y, where capital X is a function of small x only and capital Y is a function of y only. When we plug this into this equation, the equation becomes minus h line square by twice m, then the y d2x dx2 plus x d2y dy2 is equal to E times capital X and capital Y. For non-trivial solution, we divide both the sides by capital XY and multiply this one with this, or we get 1 by x d2x dx2 plus 1 by y d2y dy2 is equal to minus 2m E upon h line square. Since x and y motions are independent, we can write it as minus 2m h line square E of x plus E of y. That is, we write the total energy of the particle as the sum of its energy due to x motion and y motion. Since the x and y motion are not correlated, we can write it always. Or another way of writing it is to introduce this as minus k square, where k square is equal to twice me upon h line square. We write it as 1 upon x d2x dx2 is equal to minus this one Now left hand side is a function of x only, and right hand side, we write this right hand side as kx square. So that the x motion comes out to be d2x dx2 plus kx square capital X is equal to 0, and the y motion comes out to be d2y dy2 plus k square minus kx square y is equal to 0. We may call it ky square, so that we write it as kx square plus ky square, where kx is equal to kx square is equal to twice mex upon h line square, and ky square is equal to twice mey by h line square. Now for free particle, we assume its solution to be x of x as ax e to the power plus I kxx plus bx e to the power minus I kxx, and for these we write y of y What does it mean? It represents a plane wave moving along the positive x direction. So if we consider this is the xy coordinate system, a plane wave moving along this positive x direction is denoted by e to the plus I kxx. A plane wave moving along the negative x direction is denoted by e to the power minus I kxx. A plane wave traveling along positive y direction is denoted by e to the power I ky y, and a wave travel. So this is a wave traveling in this direction, and a plane wave traveling in negative y direction is denoted by e to the power minus I ky y. So the x direction, the motion in x direction is governed by the wave vector kx, and that in the y direction is governed by ky. The greater the energy Ex, then the kx will have greater value. Similarly for ky. Since there is no restriction on the allowed values of kx and ky, any real kx and ky values are allowed. Since any real kx, ky value can be allowed, so the energy is continuous. The energy of the particle is continuous. So there is no quantization as we have seen in the case of one-dimensional free particle. So we write the you note that one thing, that this energy value, this wave function depends on kx, so it is legitimate to introduce a continuous suffix. So the wave function becomes psi, it depends on the wave vector kx and ky as some normalization constants. Sorry, it is x and on putting this value we get the result. So this is the energy value, and the energy spectrum is continuous with the corresponding energy. It has a corresponding energy k square. The state has an energy k square given as kx square plus ky square, where kx ky belongs to a real quantity. That's all about 2D free particle. Now we shall apply the theory to a particle confined in a two-dimensional box in Cartesian coordinate system. So the basic I request you to note these two equations only. These two equations will be of help. Now, a particle in 2D rectangular box, 2D in infinite rectangular box. Let me first describe the system. The system rectangular box, we have a rectangular box of length Lx. This is the origin, this is Lx, this is Ly. A particle of mass m is subjected into the box so that the potential is zero within the box and infinite everywhere. Potential is infinite everywhere. So the system is initialized in such a way that a particle of mass m is kept within the box. What our question is, what are the possible energy values? So this we have considered V to be 0 within the well, and it shoots up to infinity on the well itself. So basically, if we apply the Schrodinger equation within the well, these are the Schrodinger equation. So one can decouple time independent Schrodinger equation within the well as, we call it a rectangular well because Lx and Ly are not same. If Lx and Ly happens to be same, we should call off square potential well. This is x double dot plus kx square x is equal to 0, where let me write second equation. Where k square is equal to kx square plus ky square with kx square is equal to twice m ex upon h line square. Ky square is equal to twice m ey upon h line square, and total energy E of the system is related to E is equal to h line square k square by twice m. That's all we have done here. Now what will be the solution? In this case, consider the particle. It is moving towards the right and gets reflected from this, because the potential shoots up to infinity. So if the particle experiences an impulsive force at all of its boundaries, and it gets reflected back and forth between the well. So the stationary waves, a two-dimensional stationary wave, will be created within this well. That's why we will not assume the solution in the term of progressive wave, rather we shall assume the solution in the form of stationary waves. So we write the solution as ax sine kxx plus bx cos kxx, and for y motion we assume the solution again in the form of stationary waves. These are the solutions. I request the listener to note again the difference between the two solutions opted in the two different cases. Although the differential equation in both the cases are same, for free particle there is no chance of getting wave reflected from any continuities of the potential. That's why we have written the solution in the term of progressive wave. But here is a chance that here where the particles gets reflected from the boundary, so two-dimensional stationary waves are formed, so that we have assumed the solution in the form of stationary waves. Now come to the boundary condition. Since the particle is initially within the well and the potential shoots up to infinity at the walls of the well, so it is not possible for the particles to overcome the well, so the wave function should be zero outside the well. So wave function should be zero outside the well, and as well as on the walls of the well. So what we assume that the wave function, the continuity of wave function demands that the wave function should be zero on the rims of the well. That is to say, the boundary condition is psi of 0y is equal to psi of lxy is equal to psi of x0 is equal to psi of xly is equal to 0. These are the boundary conditions in terms of wave function. If we write the boundary condition in terms of x and y function, it is x at 0 is equal to 0 is equal to x at lx, and y at 0 is equal to 0 is equal to y at ly. This is the boundary condition. This is the boundary condition in terms of the wave function, and if we consider these are the boundary condition in terms of the components. What this condition leads? This condition says that the coefficient related to cost part is 0. So bx is equal to 0. Bx is equal to 0. If we put x is equal to 0, this goes and this is bx, and as it has to be 0, it is 0. Similarly, this gives you by is equal to 0. And what this condition is, this condition gives you the quantization. That is, it says that sine kx lx is equal to 0, so it is equal to nx pi. So kx lx is equal to some integer nx times pi, where nx is equal to 1, 2, 3 and onwards. And similarly this condition demands that ky ly is equal to ny pi, again ny is equal to 1, 2 and so on and so forth. 0 is excluded because 0 leads to the trivial solution. So it becomes legitimate to write kx with an augmentation of nx, and it is governed by nx pi by lx. Similarly, ky is written as so what is the energy level? Now energy level is this. You see that energy is governed by E square. E is equal to h line square k square by twice m. So this is h line square by twice m taken common. This is kx square. Here this is kx nx square plus ky is again quantized. So we see that for a particular in a 2D well, the momentum is quantized. The momentum values can be taken as the integral in the quantization unit of k value is this pi by lx, and that is pi by ly. If we multiply this by h cross, we will get the corresponding momentums. Then this can be written as pi square h line square, because we use this result. It is nx square by lx square plus ny square by ly square. This is the energy value. So we write E as E of nx and y. So the energy is quantized and is denoted by two quantum numbers nx and y, ny. The energy levels, the ground state energy corresponds to 1 value of nx and ny. A particularly interesting situation arises for a square well. Let me for a square well, Lx is equal to Ly is equal to L, in which case E of an x and y is equal to pi square h line square twice L square nx square ny square. So this is the Na. We consider a state, say the ground state. E11 is the ground state, and the wave function is psi11. Oh, we haven't written the psi wave function. Let me write the corresponding wave function. Nx, ny, xy is equal to normalization constant, for which we know that 2 times Lx Ly sine of nx pi Lx x sine of and for let me first write the corresponding wave function. The corresponding wave function is nx ny xy is equal to 2 upon L sine of nx pi x by L sine of ny phi y by L. This is the wave function. What will be the wave function? What is the form of the wave function? The form of the wave function, if you take the projection along x-axis, then we write that x and this is Lx. For ground state, the wave function is this. For the first excited states, this is the wave function. This is in x is equal to 1. This is in x is equal to 2. Similar behavior will be obtained for y direction too. This is capital Y and this is x, this is y. This is for ground state and this is for excited states. This is ny is equal to 1, this is ny is equal to 2. What will be the combined wave function look like? The combined wave function, I insist the listener to draw three-dimensional plots using either GNU plot sorry, or matplotlib to see the wave form of the wave function. The form of the wave function, the ground state wave function, will be look like it will be 0 on its rims and will go in this fashion alone, and in here it is in this fashion. That is, the wave function will look like the form of a rectangular membrane. It's first and at its rim when set into vibration will give you the form of the wave function. You can see any book on acoustics, especially I refer the book due to King. The King book, there are few nice pictures of the vibration of rectangular membranes. Otherwise, you can draw the graphs of yourself or you can consult net. But now come to this point, the ground state. The ground state is E11 is the ground state. And the corresponding wave function is psi 11. Now you come to the next state. The next state is the first excited state is obtained when either nx or ny is 2 and the other one is 1. In that case, so the energy is 1 2 is equal to E21 for the square wave, and they have the same energy but corresponds to two wave functions psi 12 and psi 21. So if we consider two sets, one comprising of the eigenvalues and other one is the eigenfunctions, then there is 1 to 2 mapping, and we call it that this energy level is twofold degenerate. And this energy level is non-degenerate. You might be familiar with the concept of degeneracy in connection with the vector atom model of hydrogen atom. For rectangular, well, in general there is no degeneracy. But when we come to the square wave, this is a question of degeneration. If both the quantum numbers are same, then the energy level is non-degenerate. And when the quantum numbers are different for two-dimensional wave, the wave functions are twofold degenerate. Sorry, it is twofold degenerate. The twofold degenerate. In the case of when we shall consider the similar situation in 3D, we shall see that the degeneracy may increase to still higher values. That's all for the For today we have worked out two problems in two-dimensional case. The two-dimensional free particle in Cartesian coordinate and two-dimensional infinite potential well. The conclusion is that whenever we are subjected to a particle in 2D, for free particle there is no restriction on energy values, so the energy spectrum is continuous, and when we consider the particles confined within a rectangular or square well, the particle energy becomes quantized, and the quantization rules are very simple. Instead of having infinite well, if we had a finite potential well, then there will also be the quantization, but the quantization unit will not be as simple as this. As for example, we consider an infinite potential well and the corresponding finite potential well. There is the difference between the energy levels. An infinite potential well can support infinite number of bound states, but a finite potential well supports only finite number of bound states, and that depends on the depth of the well or on the strength of the well. Similar situation can also be applied over here, but the situation will be complicated. That's why I am avoiding this. In the next class we shall consider a free particle in r theta coordinates and a particle subjected to a cylindrical coordinate, cylindrical infinite potential well will be the topic that will be discussed in the next class.